Hello everyone, welcome to another video in the Raspberry Pi 4 assembly programming tutorial series for bare metal programming, that is. So we have worked diligently and we have gotten to the point where we can blink an LED light on and off. Very exciting stuff. However, we hard coded it. We hard coded the pin we were using and we hard coded a time. Now in the last video we generalized the pin part of it and we implemented this GPIO include file and we were able to do all the math that we wanted to do. And the last one that we actually worked with was the activity, or the whether or not the board was active LED. It's the little green one next to the power LED, and that was number 42. So we have this saved so we don't forget it. Let's switch over to GPIO 3. To refresh your memory, if you've forgotten, GPIO 3 is up here. So we'll actually be using these two pins. This will be our power source, I guess, when the pin is turned on, and this will be our ground. Now, specifically in this video, what we're going to do is we are going to work with making this actually a real time. Right now it's just a large number, and who knows how long it actually is waiting for. It seems like it's close to a second. Maybe it's a second and a half, a second and a third. I don't really know. That's what we're going to rectify. We're going to actually know how fast our delay is. So let's get started. We'll call it milli delay since it'll be in milliseconds, and x0 will be the delay time in milliseconds that we want to wait. Now, the first thing we need to do is we need to reference a clock. There's lots of different clocks on this board. The SD card reader might be at one clock, the mini UART might be at a different one. We need to find a clock that we can work with. So what we'll actually do is use MRS, and in X2 we will put in this. Very similar to what we did up here in a previous video. We're taking a system register and we're pulling its value. Now what is CNT FRQ EL0? This is what it is. It is the counter timer frequency register. Now you can see that it's 64-bit. We use X registers to access it, MRS again. However, the top 32 bits are reserved, which means they technically can use them for whatever they want. And it doesn't guarantee that they're going to be 0. So we want to clean that up a little bit. We want to ensure that these are 0. And we can also see that our counter clock frequency is in hertz. So whatever number this is, it's in hertz. Now, back in the olden days, way back when, instead of using hertz, they used CPS, or cycles per second. Clever people naming things what they are. However, now we use hertz. We will be timing in milliseconds, so we will want to know cycles per millisecond. And I don't know if millihertz is a real term or not. Maybe it is. Anyway though, whatever number this is, we will want to divide it by 1,000 because we want to convert it from cycles per second to cycles per millisecond, which is 1,000th of a second. So let's look at this. We have captured this value with this line of code. Next, what we want to do is get rid of this stuff, force it to 0, and we will use bit masking to do that. Now, I've talked about bit masking a few times in multiple videos, so I'm not really going to go into great depth of how this works. If you're confused on bit masking, please watch some of the other videos. I believe personally that they'll be very informative. Now, what this specific number is it is 32 ones all in a row, and we will AND them to finish our bit mask. All right, we are done using x3. We did want to, so this is going to be cycles per second. We want to know cycles per millisecond. So what we'll do is we will move into x3 now that we're done using it, the number 1000, and that'll give us cycles per millisecond. And we'll do UDIV, something we haven't looked at before. So this is the equivalent of x2 equals x2 divided by x3. Let's look at UDIV real quick, because you might be wondering, why is there a U in front of it? UDIV is unsigned divide, and it describes what we just described before, and it says it's using an unsigned integer value, and it puts in the destination register, flags are not affected. All very good information. Now, we have not talked about signed and unsigned yet, so let's talk about that briefly. If we look at the binary number 0, and then we have 1, and we have 2, and we have 3, and that's as far as we really need to go, I think, for this explanation. We can also have, if it is signed, this is -1. So signing gives us the ability to work with negative numbers. The reason it's called signed is this most significant bit, the leftmost bit, is our sign, I guess you could say. If it's a 1, that means it's negative. If it's a 0, that means it's positive. So let's prove this out first and look at the math and see if it makes sense. We'll take 1 plus 2 and see what we get. That equals 2. That equals 1. And we know that 1 plus 0 is 1. There's nothing to carry. We know that 1 plus 0 is 1. Nothing to carry. And automatically inserted tabs for me. Clever machine. That's not what I wanted, though. All right. So 1 and 1, or 0 and 1, 1, 1 and 0, 1, 0, 0, 0, 0, 0, 0. Okay, and that gives us the number 3. Let's change this once to be, what we're saying is -1, and let's see what happens. So 1 and 1 give us a 1, 0. So we have to carry that 1, just like 9 plus 1 gives us 1, 0 in decimal. And we have to carry a 1. 1 and 1 give us yet another 0. And we have to carry a 1. This auto tab thing is not super enjoyable that it's doing, but carrying on. It will repeat that same process multiple times here. All right, we get to the last one. 1 and 1 give us 1, 0. So we put the 0 and we carry a 1, but there's nowhere to put the 1. So we throw it away. Well, actually, we set a flag saying that we have overflowed. But if we look at this result, you can see it's all zeros, which is 0. Which means that this number plus this number actually do equal 0 when you take whatever that was in that carrying and you throw it away. So that is how 2's complement works. 2's complement is the name that we use for working with negative numbers. Well, actually, I guess that's the process of doing the math and the conversion and everything. Yeah, it's how we handle negative numbers. That's a good way to put it. So something interesting happens, though. If we look at unsigned numbers, which is what we've looked at up to this point, this is 0 and this is 15 when it's unsigned. However, now we're working with different numbers when it's signed because this becomes negative. So when it's signed, our range changes. This cannot be a 1 or else it becomes negative. So that's a 0. And then this becomes our largest number that we can have, positive 7. And this is the largest negative number we can have when it's a nibble. Obviously, when it's a byte, there's more bits, and then when it's 32-bit, there's even more, and 64 even more. And that's how all the numbers work. So obviously, that's not. Don't get hung up on that. But when working with a nibble, the largest we can have is 7, and the smallest is -8. Now, you might be wondering, how does this equal -8? Well, there's a conversion process that we can do. But first, let's add these together. They're on top of each other, so we know that it would turn into all 1s, and we've proven that all 1s is -1. And indeed, -8 plus 7 does give us -1. Let's look at the conversion process real quick, though, because it's very clever. If we start with the number 1, what we do is we knot it. So anything that was a 0 becomes a 1. Anything that was a 1 becomes a 0. Then we add 1 to it. And that gives us our -1 value. Now let's say we want to make -1 positive again. We knot it. And then we add 1. And we've just converted +1 to -1 to +1. Very clever system, whoever figured it out. Very smart, but anyway, that's the difference between signed and unsigned. The range stays the same. This is still a range of 15, but our positive maximum value is reduced because we are using this to describe negative values as well, the most significant bit. I think that's good enough for explaining signed and unsigned. Anyway, what that has done is, actually, this is cycles per millisecond. That was just our divisor that we had before. So we know how many cycles will happen in a millisecond. Let's make up some fictitious values. Let's imagine that it was 1,000,000 cycles per second. When we divide that by 1,000, we will end up with 1,000. So we could say there's 1,000 cycles per millisecond, and let's say they want to wait 3 milliseconds. So we know that in 1 millisecond there'll be 1,000 cycles, which means that when we multiply it by that 3 that the user's providing, we end up with 3,000. So what we need to do is some simple multiplication. And to multiply, we will take x2 and we'll multiply it by the user value. And we will be storing it into x2. And to learn about multiplication, it is also in our wonderful little guide that we have showing that we can multiply numbers together. And this is what it looks like. The destination equals one number multiplied by the other number. It works with both W-type registers and X-type registers, so both 32 and 64-bit. Very cool stuff. So we have total cycles that need to elapse. And it's really handy, actually, that we can divide and multiply. I remember doing assembly on a Z80 processor, and there was no multiplication, so you had to write your own algorithms to multiply. And division, yeah, division is not fun at all. So, wonderful, wonderful things that we have here. Anyway, we are now at the point where we know how many cycles need to elapse, but we need to have it fixed to something. We need a counter, and there is a counter. So if we look at our frequency, you can see this is the counter timer frequency register. There's another one in here called CNT PCT, and this is the counter timer physical count register. So the minute the chip boots up and starts running, it starts counting. So if we had that example before where we had 1,000,000 cycles per second, in the first second this will become the number 1,000,000. After 2 seconds this will become the number 2,000,000. And obviously it's not tied specifically to per second. Every time the clock pulses, it's going to add 1 to this. And then once it's completely full, it will overflow and become zeros again and count up from there. We're not going to count that interesting edge case in our simple little timer here. We're not going to check to see if when we add these together, if it's close to 0, which means we're going to overflow and whatever else. We're not going to accommodate that. Hopefully that'll be an extremely rare occurrence. Now, if you were writing something that's like life safety or something else, these are things that you have to consider. We're blinking an LED light on and off. I think we're going to be pretty safe with what we're working with. So anyway, we need to capture the initial value. What is this value when we first start working? So we'll come in here, and in X1, we will put in that CNT PCT EL0 value. So how much time has elapsed since startup? Okay. So we need to figure out our total time now. We have an initial time and how much needs to elapse. So we're going to add those two numbers together. And we'll store it in X2, and we'll take X1 and X2 and add them together. So if this started out at 1,000,000 and we need to add 3,000, we'll end up with 1,003,000. And now what we need to do is start checking things. Something I want to talk about is namespacing, and we're going to actually do a little of that. So we have milli delay, and we're going to start with a period for our label. We'll call it delay check. And I'm going to do a branch right now. This will change a little bit, but I want to explain this while we're here. So we could just call it delay check without a period in front of it. But what this period essentially is doing is it creates a label like this. And I think that this is beneficial because if we want to ever have another delay check, let's say, and actually we will do this because it's really easy once this is done, we will make a micro delay where it's in microseconds instead of milliseconds. We don't have to name this something super unique like micro delay check. It's in a namespace in a way. It allows us from not having to create super unique names. Like if we wanted to have the word exit in here somewhere, we don't have to call it milli delay function exit or something. We can just put period exit and it's scoped in that way. All right, anyway, back to this delay check. So where were we? We looked at how much time we started with. We've added how much time we need to wait. Now we need to check how much time has actually elapsed. So again, we are done with X1, so we can reuse that. We needed it to find out how much time we need total, but that's saved in X2. So we will basically copy this line from above. And now we're going to do a comparison. We're going to compare X2 to X1. And if X2 is greater than x1, we're going to run this again and check again and see where we're at. So originally I said we were at, let's say, 1,000,000. We need to get to 1,003,000. So let's say we're at 1,002,000. It will check this. It'll say you're at 1,002,000, and 1,003,000 is greater than 1,002,000. So it will run this again. And let's say now it actually is 1,003,000. And it will do the comparison, and it's not greater than, so it will escape. And just like here, we need to do a return. So now we have a milli delay. So let's replace our logic here a little bit. What we need to do is, I thought I had this in my notes. I guess I'm going to have to do it off the cuff. We will add in here that we want to wait 2 full seconds, so 2,000 milliseconds. So into x0, we will be moving in 2,000. And then we will branch to our milli delay. We don't actually need this anymore. And in the last video, I talked about how we were going to move. Every time we ran one of these, we were going to always move the GPIO base back into x0. Yeah, I found that out when I just assumed that it was going to stay x0, and I added this, and I tried going to address 2000 instead of where it needed to be. So that's why we wrote that. That was learned from experience. And it took a little while to debug. So obviously, even when you're writing things like this, wherever you can, it's always worth stopping, compiling, testing, however you can, because otherwise it can be a challenge sometimes, especially when we're first starting out with a lot of basic code things where we're not calling this type of thing very often, and we're kind of building our tools that we're going to be using. All right, so we have this set up. We're going to turn on 3. We're going to wait 2,000 milliseconds. So we jump here. When we're done, we come back, turn it off, wait 2,000 milliseconds, repeat for infinitum. And I do have notes over on the side here. I want to make sure that I have written all of this out and not accidentally transposed something or made a mistake, because only want to give you guys the best content possible. Okay, yep, everything matches. So we'll save this. We will assemble it. It built. All right, very good. So let's test this out and see what happens. Okay, so let's test it out here in real life. If we plug in the Raspberry Pi, it'll take a second to boot up. We're on pin 3, so it starts out lit up already. And if I listen to the clock in the room, oh, that's amazing. It is perfectly in sync to the second, at least to human ears. So we have succeeded. Okay, very cool. Next, let's test it out with a 1,000 millisecond delay. So it'll only go 1 second instead. Save that, build it, and let's test that one out. Okay, so let's test this one out in real life and see how it fares. It should be twice as fast as what it was before. Now that our clock is tied to the CPU, it should be accurate to the second. And Yes, it is. All right, so very good. It works in real life. All right, very good. That worked as well. So I talked about microsecond delay. We've already done this millisecond delay. What we're going to do is we're going to just duplicate this, and we will call it micro delay because we may want this in the future. We don't have to worry about renaming any of this stuff because of this little period. Super handy, I think, personally. But we do have to tweak this a little bit. And what we're going to have is we do have cycles per millisecond. We're going to multiply it. And then x3 is still untouched. So let's run this again. So this will be total cycles. And total cycles in microseconds. All right, and that should be microseconds. So the way it'll work is everything is exactly the same. We calculate our oops, that's not total cycles. The total cycles is actually here when we add again. This would be elapsed cycles in microseconds. Okay, so we have our cycles per second. We clean it up, divide it by 1,000. That gives us cycles per millisecond. Now we could just divide it by 1,000 again, but if just in case we have an absolutely tiny number and the user puts in a really large number, I don't want it to truncate our value. So we will actually multiply in their value, and then we'll divide out the next 1,000 after that. That will tell us our total cycles, and all of this other stuff remains exactly the same. Let's also make this an include file. Now notice that these are functions because there's a fun little issue we're going to run into that we have to also fix. Call this timers. Include. We're going to just cut this out. And let's actually nest it one more deep. So we'll call it timers. We'll put a period in front of these. This does allow for a small caveat though. We have to add this level of detail. Now we could get around this if we look at the documentation. If we were to put in the namespace and then put in an end namespace when we were done with it or whatever, but I don't want to. I just don't want to actually deal with that. So if you are interested in doing it that way, highly recommend the documentation. They explain all these different things with namespacing and all that. Now this will change things a little bit because now we are using timers. We will duplicate this. And the funny thing is it's timers dot. Thing is, this will build, or at least it should. Yes, it does. But there's an issue. We start at address 80,000, and we didn't have any of these types of functions with actual code. They're macros, so this is kind of like a find and replace. This is actual code. So at 80,000, it will drop in all of this stuff Now remember, our code starts running at 80,000, so it's going to try to run all the timers with whatever the default value for x0 is. And then it will finally get to what we care about. So what we want to do is skip over this. I'm going to just call it start, and I'm going to say branch to start. So this will allow us to skip anything we have in between, and it will allow us to still branch on over to where we expect things to work. So it'll come in, jump to here, and this gap, as we add more and more of this type of code, will widen more and more, but it will jump over all that. Are there ways around that? Sure, we could include it at the bottom, but I like including everything at the top. Now we don't have any header guards. We'll talk about that in another video. This video's gone on long enough, I do believe. Anyway, though, we now have the ability to work with millisecond and microsecond. So I hope you found this video enjoyable, and we look forward to seeing you in the next video.